Hello, and welcome to our program, Astronomy for Everyone. The topic of this month's show is life outside of our solar system. Joining me here in the studio to talk about this topic is our own Tim Day. Tim, welcome back to the program.
Thank you, Don. It's always a pleasure to be here.
Good. Well, in our February show, we ran a program that we had broadcast last year, Life Within Our Solar System. We rebroadcast that show to have it work as a lead-in for this month's topic, life outside the solar system. But Tim, I think we should take a couple of minutes perhaps and recap last month's show for those folks who haven't had a chance to already see it.
Sure, let's do that briefly. Last show, we were looking for life outside of the planet and checking out each of the moons or planets that come from the sun all the way out to Pluto and beyond.
So we know, for example, that on Earth, our home planet, not only do we have life that's sitting here talking to each other, but we've also found life in some very extreme locations.
We have. We're not expecting little green men to be in our solar system or the first thing that we find, but we are looking for life in some form, even if it's just microbial. So our planet is covered with liquid water, and that's just such an essential element in the hunt for life as far as biologists are concerned. Water that's not frozen or steam is the perfect medium for molecules to meet each other and to arrange themselves in chains that might then begin to reproduce themselves. It's just an exciting medium to find elsewhere.
Now, these extreme areas on our planet include some deep water seeps, thousands of miles or feet below the surface. They found microbes in ice, so that seems to change the equation in a bit of bacteria.
It does. So again, we're looking for liquid water, but we're willing to give it a lot more. We're willing to give life a lot more slack, if you will, as we imagine what are the extremes it can tolerate and still be present.
Speaking of extremes, looking for life off of our home planet, searching on Mars, which we've been doing extensively for decades, and a couple of other places that might be good sources are Europa, one of the largest moons of Jupiter, and Titan, the biggest moon of Saturn.
Exciting times, great things to be looking at. Nobody ever thought we'd be looking at Jovian or Saturnian moons before. We thought, hey, life has got to be on a planet because that's what is our case on Earth. It's on a planet. So we last time took a quick look at Mercury, very hot. Venus, nice distance, same as Earth size, but full of sulfuric acid, not very nice. Earth accounts for us. Mars, we were really hopeful. We still are. We're looking, but we're still looking. And it's been some while now. There may be life. There might have been life. We're just not sure yet. We continue to investigate. Then it comes to Jupiter and Saturn and Uranus and Neptune, and these are gas giants. We don't expect life to be on those planets or in those atmospheres, but the moons that go around them are so large, they rival some of our own planets like Mercury. They may be candidates. Some of them have oceans under ice. There are all sorts of possibilities we never thought of before.
Interesting times. Interesting times.
Again, yes, indeed.
Now, we've been searching for planets outside of our solar system for, about the last 25 years. And I assume the techniques have gotten better over the years. How did they start?
They have indeed. This picture is just an artist's graphic rendition of a solar system that's young, that might be forming new planets where we might start looking for life. But until the late 1980s, that's all we had, just artists' ideas, scientists, theories, but no positive proof that there were even planets at all outside of our solar system. So the first step was, let's discover some planets. Well, planets away from our own solar system are going to be very dim. It took us a long time even to find Pluto and some of the other Kuiper Belt planets that we now know are here just recently. So what we're looking for are very, very dim points of light, planets around other stars. And in fact, we haven't even seen too many planets directly. What we've seen are stars behaving a little differently than we might expect. And so giving us hints, let's look here for the possibility of planets. So here's a picture of a star called Fomalhaut. And around that star, there are pictures of a tiny, tiny dot of light that's slowly moving on. You can see 2004, 2006, 2010, 2012. You can see that little point. That's actually a planet. It is obviously very, very faint. And it's next to a very, very bright light source, its own star. The trick is for us to take a mask, a little circle, blank out most of the light from the parent star, and now the fainter things all the way around the edge begin to get visible for the first time.
Now, this was a visible light discovery.
It was indeed.
But a lot of them aren't.
A lot of them aren't. So if we're looking at the visible light of a star, not the planet itself especially, but with the star, we need to have a big, big light collecting bucket, a dish. And so on the top of places like Hawaii or in Antarctica or places where there's nice high mountains and clean sky and dark skies, we'll use telescopes like this one. This is the Subaru telescope. That's a Japanese word that means the seven sisters after the stars in our own northern hemisphere. And the mirror is over 8 meters across. It's enormous. It's able to see very, very faint things like distant galaxies or, in this case, very faint planets.
Now, this technique, here we can see a photo of the Kepler space mission.
This is a space telescope. Think Hubble when you think of this instrument. So it's away from our own atmosphere, which makes it so hard to see small motions or faint things. Mm-hmm. And it has done a spectacular job of looking for new planets. So the Kepler Space Telescope is out there, it's looking, and it's really increased our ability to detect very faint planets, very faint points of light, or stars that are dancing just a little bit as the planets go around them and tug them left or right or closer and further.
Okay, and Kepler was actually looking at a fairly small patch of sky towards the constellation Cygnus, and yet its results have been outstanding.
Again, it's sort of like the Hubble deep space images where nobody expected to stare at an empty patch of sky and see just nonstop galaxies, no matter how far we look.
Such as this image here.
Such as this image here. So that little red dot is a very, very faint galaxy, a very bright object if you're close or you're in it. But for us, it's as far as we can see something that's bright, but very, very far away. Another way to look for life or to look for information about stars, listen for things, is to listen in the radio frequencies. This is an image of an enormous listening device. It's a telescope for hearing radio waves. The advantage to that is that radio waves can travel through places that regular light can't, like dust clouds or from places that would otherwise be hard to see with an optical telescope.
And that was the Arecibo radio telescope in Puerto Rico.
That was the Arecibo in Puerto Rico. And it will come up again in our story as we talk about the earliest search for life.
Now, I understand we have a couple of images and graphs. This particular one right here, what is this showing us?
This is a graph of how many planets have been found since 1988 or 89 when we discovered our very first hot Jupiters, the big, big planets that are closest to their stars. And you can see 1989 was the first, then none, and then a couple more, and so like that. And then all of a sudden that graph just goes way up. And that represents 2014. You can see the number of planets we're discovering outside of our own system, solar system, is just growing enormously. It's an exciting time.
In the second part of our program here after our quick break, which comes up in just a few minutes. I think we have some images of showing folks just how the techniques work that these space scientists have used using telescopes such as the Arecibo and the Kepler to detect the motion of the parent star. So we'll save that for the second part. Coming up next is, of course, our own Stephen Whitty with Term of the Month. If you have a question, as always, please send us an email. We look forward to reading those. And as I just mentioned, coming up next is Stephen Whitty with Term of the Month. Take it away.
Term of the month for March 2016 is Planet 9. So Planet 9 doesn't, in fact, exist as far as we know yet. It is hypothesized to exist. If it exists, it is half the size of Neptune, and it has this really big orbit. And we don't know where exactly it is on this really big orbit, so we don't know where to look along the possible orbit. There is a report now from the French saying that they have calculated that we can eliminate half of the orbit, so we can reduce the search. The reason why we think it might exist is because of the orbits of objects that we do know. So these are off to the left here, Sedna, and a bunch of telephone number objects. And they have these peculiar orbits. And if there is a big planet, like Planet 9, in a particular orbit, then it explains why these other objects have the orbits that they do. And that is the term of the month for March 2016. Back to you, Don.
Thanks, Stephen. We're going to continue our discussion about life outside of our solar system. Joining us is Tim Day, one of our own club members and crew members as well. Now, there are some techniques, specific techniques, that are used to discover these planets around these distant stars. Can we talk a bit about that?
We can. The stars, of course, that have planets are far away from us, but they're relatively easy for us to see because they're so bright. The planets are much dimmer, or they're hiding behind the star's light. They're sort of lost in the glare. And so the earliest techniques for discovering planets, or stars with planets, was to see if the stars wiggled, to look for wiggle or wobble. Okay. And those are the first couple of techniques that we began to employ successfully.
Now, was this done in the visual mode, or was spectroscopy added as well?
Spectroscopy is visual in the sense that we're collecting the sort of light that you and I use to see things in a room. And what we notice about radiation, electromagnetic radiation like light or like sound waves in an atmosphere or through a medium, is that when the object is getting closer to us, then the waves that it emits seem to be compressed. They start to come faster, and we hear a pitch rise like a train coming at us, or we see light gets shifted into the blue part of the spectrum, and then when it goes away from us, the light gets stretched out, or the sound waves get stretched out, and we see it shift towards the red. So what happens with a star, with a big planet coming around it, is if that star is not too far from us, we will see it wiggle just a little bit. It'll either get closer or farther away. We'll get red shift or blue shift. That was one of the very earliest techniques. Similar to that, we can actually watch for stars to wiggle left and right. So we talked about closer and farther. That was the velocity and the redshift, blue shift. Now we see left and right dance. Stars and big planets, or all planets, actually circle around a common center of mass. And so that's the little bit of wiggle we see in the parent star. It's small. You have to be precise. You have to practice, but it's possible, and we're getting better at it.
I believe we have an image that illustrates that?
We do. So here's an image of a star, and the star has an imaginary planet going around it. And so you can see the planet's much smaller than the star. The amount of wiggle that planet, if they were tied by a string, would make the star move is pretty small, but it's detectable in some cases. The other thing that we can look for is if the solar system of that star and planet is right edge on to our point of view. Then what happens is the planet or planets go in front of their star on a regular basis. And if we watch carefully with instruments, we can detect the star getting just a little bit dimmer. That's the light curve part. The star has a given light constant, and then it dims just a little bit, and then, it brightens up again, and we wait, dims a little bit. It brightens up again, and we go, aha, something, not another star, keeps crossing in front of this star, and we suspect planets.
We can time that travel to...
We can,
Okay.
and we first detected big planets close to their sun. Now we can see much cooler planets out in the Goldilocks zone. This is a star system called Kepler-62, and it's exciting because it was one of the first star systems where we confirmed not just one planet, but a few planets. And some of those planets are not too close to their sun, not too far away from their sun, but just right. So on the left side of the screen, you see 62F and 62E. They're kind of blue. They might have water, and they're just the right distance. The habitable zone is the Goldilocks zone.
To have that liquid.
To have that liquid water and not to be scorched, and they're in a stable orbit, and things are comfortable, and we're very excited to continue to watch Kepler-62 in the future and see whether or not we learn more and more.
Of course, the other three planets that they were showing were much closer to their sun and presumably too hot.
Just as Mercury is too close to our sun and too hot.
Okay.
These other planets, 62F and E, are more like Venus and Earth. We tend to find big rocky planets because they're a little bit easier to find.
Okay.
But we continue to hunt, and I'm sure we'll continue to find smaller and smaller planets.
Certainly we're finding many of planets based upon this bar graph here.
Look at the far right side of that bar graph. It has all the color and it draws all your attention, and so it should. So as we've been able to detect dimming of stars being transited by the planets, that technique alone has enabled us to just discover literally hundreds of planets, where before it was just 1 or 2 or 10 in a year. So this space telescope, the Kepler, uses the ability to detect that brightening and dimming, among other techniques, to just stare and find dozens of solar systems in a year, if not more. It's an exciting time.
It sounds like we've really expanded our potential from starting here on Earth and then moving out to space with spacecraft, such as the Kepler. Where are we going in the future? What's next?
Now that we've started to get the hang of finding planets that might be detectable and in the Goldilocks zone, not too hot, not too cold, maybe there's water, we get excited. Now we have to start thinking about what percentage of those are going to have life that might have little green men on them, people who would be willing to talk to us, or life that can communicate. And so here's their typical, picture of the little green men, courtesy of Steven Spielberg. And this is the big radio telescope in Puerto Rico, Arecibo, that I mentioned earlier. And it's the instrument that was used first in a serious fashion to listen for other civilizations that might have something to say and would be using radio to say it.
Now, is there a technique or a formula that's been developed that helps us with the possibility of finding these little green men?
On the screen in front of you is a nicely smiling gentleman. His name is Dr. Freddie Drake. And he came to Arecibo as a graduate student in 1961 and wanted to do a piece of research that was new and undone and exciting to think about. And so he said, let's think about how would we guess how many civilizations might be out there? What's a reasonable scientific expectation if we begin to listen?
And we call that the Drake equation.
The Drake equation. And even though it's a good 50 years old, it's still very helpful today, and we're using it now, and it's the basis for the continuation of our discussion here.
So in a nutshell for our audience, can you run this down for us?
I'd be delighted. It's a scary looking equation, right? One letter on the left, how many, N, the number, and then 6 pieces on the right. It's easy. Please don't be intimidated by it. So the N part is the number of Milky Way galaxies, civilizations, meaning our own galaxy, that are out there and intelligent and communicating and actually trying to talk now. So what do we need to know to discover life in space? Well, I guess to start first, it's good to have a star. Well, how many stars are forming out there? We can make good estimates based on looking around our own galaxy about how fast stars are being born. They come in quickly. We have a good sense for what that rate is. It's a pretty firm number. So that's the first thing we want to know. How many stars are out there? How fast are they forming? How fast are they dying? The second one we want to think about is, okay, we've got our star, but does it have any planets or planets with moons? And so what we begin to look for is planets with moons. The next thing we want to think about is how many of those planets are Earth-like. How many are like our own planet in the Goldilocks zone? The piece after that is how many of those Earth-like planets actually had life arise on it. Not intelligent life yet, but we're getting there. Now we've got maybe unicellular life. And then of those planets that have life on them, how many actually got intelligent life? So more than just bacteria. And of the intelligent life planets, how many are wanting to talk to us, are communicating? And if they're intelligent and they're communicating, the last piece is how many are actually still talking, the length. You crunch those numbers together and you get a solid scientific answer to what do we need to know, what should we expect.
So here we have some potentially habitable worlds. Maybe we'll find something on one of those.
This picture wasn't possible till just the last few years. It's so exciting to realize that we're discovering Earth-like planets on a very frequent basis, and the chances for life seem good.
This has been a fascinating topic, and we could go on for much more than the half hour that we have. I do want to thank my guest, Tim Day, for taking the time out to discuss this with us. We'd like you to visit our website, the Ford Club website. The address is down there at the bottom of your screen, along with how to get us directly. So please visit that. We hope you've enjoyed the show, and before we end up, as always, we'll have What's Up in the Night Sky with our own Stephen Whitty.
What's up in the night sky for March 2016? The sunrise ranges from 7:07 in the morning to 7:16 in the morning, and sunset ranges from 6:23 to 7:58. This is kind of a weird disparity. It has to do with daylight savings. There are 5 phases of the moon this month. There were only 3 in February, so we've got 2. We start with the third quarter moon, and we also end with the third quarter moon, so the 1st and 31st. We have the new moon on the 8th, we have the first quarter on the 15th, we have the full moon on the 23rd. So Mercury and Venus are morning objects. Here we're showing what it looks like on the 1st of the month, and that's because Mercury is farthest from the sun. It looks the best that it's going to all of March on the 1st. It just gets worse from there. Superior conjunction for Mercury is on March 23rd. That's when Mercury and the sun will be lined up. You will not be able to see Mercury no matter what. And so we have our next farthest from the sun on April 18th, so that's not this month. Anyway, Venus rises from 6:13 to 6:48 over the period over the month, and it's getting closer to the sun as that happens. Superior conjunction, when we certainly have lost Venus altogether, is in June 3rd. So then we move to Saturn. Saturn is in Ophiuchus, that constellation. Here it is also on the 1st of March, but at 6 a.m. because we're not trying to optimize Mercury. Saturn rises from 2:15 in the morning to half hour after midnight over the course of the month. We have an opposition coming up in June 3rd. So that's the best month for Saturn. Saturn is really quite good this month. The moon happens to be in third quarter on at the beginning of the month here. So it just happens to be here in the shot. Mars is in Scorpius. It rises from almost 1 o'clock in the morning to really a half hour after 1 o'clock. Opposition is in May for Mars. Mars is getting better, and right up until late May. Jupiter, also way at the far right here, is in Leo. It has an opposition on March 8th, so it's pretty much in the sky all night long. It is the closest to Earth this month that it is all year this year. It is the biggest, and it is also brightest for Jupiter. So then, looking at the solar system from the top, the view is called an Ori view. Uranus turns out to be the only evening object, and you can tell morning objects from evening objects by the angle. Now, the inset that's in the upper right-hand corner, the third ring out, has a mark sort of at 10 o'clock there, which is the Earth. So if you look at the Earth-Sun, anything that is sort of to the right, that includes in the bigger image as well as the littler image. Everything to the right is in the evening, and everything to the left of the Earth going around that circle is in the morning. So Uranus is the only evening object. Neptune is behind the sun, so you really can't see it this month. Everything else is a morning object, but you should note that Jupiter is almost in line with the Earth and the Sun, so Jupiter is at opposition. And that's what's up in the night sky for March 2016. Now remember, here at Astronomy for Everyone, astronomy is free, but we may tax your brain.